Alright, hello everyone, welcome back to the F equals MA Club, day 10. This is going to be the 10th lecture, online lecture for our 10th week for the F equals MA Club, and today we're going to be talking about fluid mechanics. So let's get right into it. Just a little bit of review. Last time we talked about static equilibrium. This is a state where all objects are at rest and the net force and torque are at zero. Remember our talk about subsystems, where we focus on the center of mass and combining subsystems. We talked a little bit about torques and choosing an origin that eliminates the most unknown torques and unknown forces as possible, and talking about center of mass and gravity. It wasn't too big of a unit, but it's just some nice background knowledge to know. Alright, so fluid mechanics, right? So fluid mechanics is just the study of the behavior of fluids, which refers to both liquids and gases. And so there's two forms of fluid mechanics. There's fluid statics and fluid dynamics. And as you can see on the screen, the two differences is that for fluid statics, fluids are at rest, and for fluid dynamics, fluids are in motion. So like maybe in a hose or being pumped. And so this is a pretty commonly tested topic and also one of the harder ones out there, with around 2 to 3 problems per test and one of the lowest success rates on these. And so let's get straight into it. So dealing with fluids, remember to use density instead of mass, where our density is equal to our mass divided by our volume. Remember to use pressure instead of forces, and our pressure is going to be our force divided by our area. This just means perpendicular. And so this is measured in pascals or kilopascals, and this is just some extraneous information. That's just nice to know. Remember Pascal's principle, which basically means that if the force is increased, the force will be applied even, there will be an increase in force across the entirety of the area. And what this equation is trying to show is that our force is directly proportional to our area. So if our area increases, our force is going to increase. And typically we see this in these kind of hydraulic problems where this isn't too much of FMA, but just more of classic mechanics, where let's say we're just pushing down here with a force and some kind of area. If our area is very small here and we apply a force, we'll have a lot more force on this side. Our second force will be a lot greater than our first force because our area is also greater than our original area, right? And so that's why you typically see, if you search stuff like this up, something like Pascal's principle, you'll probably see a diagram like this and then some kind of car or some heavy object on this side and just a small force on this side, right? So that's the concept of Pascal's principle, and we get an equation from this, which is that our pressure is equal to our force divided by our area, which is also equal to rho, which is our density, rho times g times our height, right? And so the taller that, like for this diagram, the taller that this class is, and the more this height is, we're going to have more weight and more pressure, right? So let's move on. So buoyancy, right? So our buoyant force is going to be what our buoyancy is. So our big thing is Archimedes' principle, which is that our buoyant force is equal to rho times our volume times our gravity, right? And we also have specific gravity, which is equal to the density of our material divided by the density of our water. And you can see in this diagram what that means, right? To the right. And so that says that if our buoyant force is greater than our gravity force, then it's going to float. And so that would mean that the density of our material is less than our density of our water. And so that would be, if this value is less than 1, then it'll float. If it's equal to 1, it'll perfectly float. And then if the material's density is greater than the density of water, then it's going to sink. So something like this last one, where our gravity force is going to be a lot larger than our buoyant force, and so it's going to sink, right? So we can treat this buoyant force as an action-reaction pair, and there's also a few problems about torque of buoyancy. These are going to be a lot harder, which is why I didn't include the one problem that I saw about buoyancy and torque, which is that the buoyancy will act as the center of mass on the submerged portion of the object. So if we go back here, let's say we have some kind of object that looks kind of like this and submerged, right? our torque of our buoyancy is going to act on the center of mass of this portion of the object, right? And that's basically what that part of the notes is trying to say. And so we can also see Archimedes' principle here, where we have our buoyant force here. All right, so just a few more equations. So first we have the continuity equations. These are for something known as laminar flow, and you can see a diagram over here, and that's when our volume is constant. This has to get, or whatever, I'm pretty sure that just means velocity in Norwegian, or it's just like another term for velocity. You're not going to see this. It doesn't matter. I'm just proud that I researched this, right? And so this V, of course, is going to be velocity, not to be confused with volume. But remember that our volume is going to be constant. And so for something like this, once our area decreases, our velocity is going to increase, right? And so for Bernoulli's equation, we have this huge mess, which is pressure, our static pressure as shown before, and our and this part. And so this looks very similar to conservation of energy. And so a few conditions. Remember that it only works when viscosity is negligible, for something like water. And remember, viscosity means like the internal friction of a fluid. So to give you a kind of a description, honey has very high viscosity. It takes a long time to pour, and when you tilt it, it just flows really slowly because there's a lot of internal friction within the fluid, right? And so it's very similar to conservation of energy. And there's something known as Bernoulli's effect that is based on this, which is that if the velocity increases, the pressure will decrease. And so finally, we have Torricelli's theorem, which is our velocity is equal to the square root of 2gh, which looks kind of similar to our back to our kinematics equations, but this is where h will increase as the hole's elevation decreases. So h goes kind of inversely with the actual height, right? So if we see this, we can see that this top one will actually be the weakest jet, and this bottom one will be the strongest jet, because h in this case, which is inversely inverse to our actual elevation, is highest there, right? So I think that's about it. Let's just switch to the worksheet. All right, so first problem. Flasks A, oh my god, I can't pronounce. Flasks A, B, and C each have a circular base with a radius of 2 centimeters. An equal volume of water is poured into each flask and none overflow. Rank the force of water F on each base of the flask from greatest to least, right? So a common misconception when many people were taking this test, right? So what do we have here? We have, I'm just going to draw these out kind of roughly. So we have A, we have B, right? And we have C, right? A, B, and C. And so a common problem that a lot of the testers found was that a lot of people just said, oh, it's the same volume, right? Or something along those lines. And they just said these pressures should all be equal. That is not true, because it's an equal volume, which means that each of these is going to have a different height worth of water, right? So let's change this color a little bit. So we might have this amount of volume here, but we have the same exact volume but at a different height for B, and same exact volume but a different height for C, right? And so remember that our pressure, our static pressure, is measured by rho GH, right? And the fact that each of these has a different height means that the pressures are going to be different. So this is going to be based on the fact that that C, this is going to have a different height from A, which is going to have a different height from B, right? And remember that our area is always going to be the same for all of these, right? All with a radius of 2 centimeters, right? Circular base, which means that this area is going to stay the same. The only thing that's going to change is our force, right? And so based on that, we know that this is going to be our pressure is going to be the largest for flask C, which is going to be greater than flask A, which is going to be greater than flask B. And let me just switch over. If we look over at our worksheet, that's going to give us answer choice D, which is that our pressures, that our force for our C is going to be greater than A, which is going to be greater than B. And remember, the same concept applies, right? So our pressures are going to be different because of this equation. And since our areas are going to be the same, that means our force is going to be the same. So sorry about that little mishap, but that's basically what it's trying to say, right? All right. Next question. A container of water is sitting on a scale. Originally, the scale reads mass 1 is equal to 45 kilograms, and I'm assuming that's going to be the water, right? A block of wood is suspended from a second scale. Originally, the scale read 12 kilograms, so this block of wood. Density of wood is 0.6 grams per cubic centimeter. Density of water is 1 gram per cubic centimeter. Block of wood is lowered into the water until half the block is beneath the surface. What is the resulting reading on the scales? Right. Okay, so this is actually quite an interesting problem, right? We know that we have these initial values, right? This is displaying 45 kilograms, and this top scale is displaying 12 kilograms, right? And we have this block of wood on here. If you recall from a very long time ago, when I was very, even worse than now at teaching my lessons, I said something about springs measuring the normal force, right? Which means, well, not springs, scales. Scales measure the normal force, right? And so what that means is, as we lower this block into the water, we're going to have a buoyant force, right? And so this bottom scale is going to increase by some delta m, right? The reading's going to increase by some delta m, and the top scale is going to decrease. I'm going to put a plus, decrease by some delta m. And these are going to be the same because of the buoyant force, right? It's the same buoyant force acting. And so let's determine what this delta m is. And we can first say that our mass is going to be equal to rho vg, right? Our rho v, right? It's going to be our buoyancy divided by our gravity, because our buoyancy force, remember buoyancy force, is equal to rho vg, and we know that density is equal to mass divided by volume, and we can just use a little bit of math to determine that mass equals our density times our volume, which we can plug back in here. So that means that our buoyancy force is going to be, our mass is going to be our buoyancy force divided by our gravity, right? Or our gravitational acceleration. So let's determine what our buoyant force is then, right? So our buoyant force, remember that our block of wood is going to be lowered until half the block is beneath the surface, right? So we're going to go by rho, which is going to be the rho of our water, right? Times V, which is actually going to be 1/2 times the volume of our block, right? Because only half of it is submerged, times G, right? And so we can start simplifying this. What's our volume going to be? Our volume is going to be, I'm blanking out. That's going to be our mass divided by our density, right? Again, back to this equation, we can just swap these two, and that's how we get that. So what our volume is going to definitely be of the wood, not our water. So that's going to be our mass 2, and the rho of the density of our wood. Sorry, and so that means that our buoyant force is going to be the rho of our water, the density of our water, times 1/2 times mass 2 divided by the rho of our wood times gravity, right? And so we can say that this is equal to rho water times mass of m2 times g divided by 2 times the rho of our wood, right? And so I'm gonna select all of this, move this to the side, and that is a rho button, right? So let's move this all to the side. And so now we know that our mass, our change in mass is going to be equal to the buoyant force divided by our gravity, so we can just cancel that out. So that means that this is going to be equal to the density of our water times the mass of our wood block divided by 2 times the density of our wood, right? And now we can just start plugging in values. So the density of water is equal to 1 gram per cubic centimeter, so that's going to be 1 times our mass 2, which is 12, divided by 0.6 times 2, right? So that's 1.2. So that's going to be equal to 10, right? 10 kilograms. And so our change in mass is going to be 10 kilograms. We know that the water is going to gain this delta m, and the scale for the wood is going to subtract that delta m. So that means that our final readings are going to be 55 kilograms for our first spring, for our first scale, I'm just going to measure that. And for our second scale, it's going to measure 2 kilograms, right? Remember that the buoyant force is pushing it up, so it's going to change by this much, right? And if we look back at our worksheet, that's going to give us, answer choice. Did I do this wrong? Yeah, answer choice E. Answer choice E. Right. Let me double check. My broken answer key says something else. So, give me just one moment to double check everything. Yeah, okay, so it's E. I wrote it down wrong. But yeah, let's go back here, go to our worksheet, and we can start working on problem 3. So, this was actually listed as one of the harder problems, which surprised me because it's not actually too difficult if you think everything through. But, okay, let's go through the general premise of this problem. A 3 centimeter thick layer of oil with density 800 kilograms per meter cubed is floating above water that has density of 1,000 kilograms per cubic meter. Solid cylinder is floating so that 1/3 is in the water, 1/3 is in oil, and 1/3 is in air. Additional oil is added into the until the cylinder is only floating in oil. What fraction of the cylinder is in oil? So we know that this 3 centimeter probably isn't going to do much, right? It's only asking what fraction of the cylinder. They don't give any heights. Don't ask for like the final height of the oil or something like that. So let's just start working on this, right? We know that our mass of our cylinder, right? The mass of our cylinder, which is going to be m. Let's just do mg. Is going to be equal to, well, like the gravitational force acting on our cylinder is going to be equal to the buoyant force that's pushing it up, right? So that's going to be, what is our buoyant force? So we have 1/3 of the rho of our the density of our water times Vg, and you can probably understand why that's 1/3 because it's 1/3 of the volume of the cylinder is within water, and 1/3 of it is within oil, and I'm just going to label that O. Looks like a knot. That's not what I'm going for. We can cross out all these G's, and we can factor this out. So this is 1/3 times V times the density of our water plus the density of our oil, right? They actually give us that this is a W, but I'm just going to write this as H2O for now. All right, so we can now say that our final, that this current, sorry, what am I trying to say? So, the current buoyancy force is going to be equal to the final buoyancy force, right? Buoyancy force isn't going to change, but what if we change this into the buoyancy force of oil? So, this is going to be after we pour in all the oil, this is going to be before we pour in the oil. And this rho is going to actually be equal to mass divided by volume, right? So we can just divide volume by both sides, cancel this out, and now we have that rho is equal to 1/3 times the density of our water plus the density of our wood, right? So that means that we can say that there's a fraction here, right? Because it's asking for what fraction of the cylinder is submerged in the oil after it's filled completely with oil, or after it's floating in oil, right? And so that means that we can just start plugging in values and try and find what this constant is going to be. So see, we can cross these out. So this is just going to be our density here divided by the density of our oil, which is going to be equal to 1/3 times our water plus our oil, right? That's the wrong symbol, right? All this divided by 3 times the rho of our oil, right? And if we plug this all in, I'm pretty sure that's going to give us 1800 divided by 3 times 800. So 3 times 800, 2400. And now we can simplify this to just say we can divide 600 on either side. And so that's going to give us 3/4. And if I'm correct, that is going to give us our answer, which is, if we go back to our worksheet, that's going to give us B, which is 3/4, right? All right. Sorry, wrong function. So next, a sphere floats in the water. This is a simple one. A sphere floats in the water with 2/3 of its volume of the sphere submerged. A sphere is removed and placed in oil that has 3/4 the density of water. If it floats in oil, what fraction of the sphere would be submerged in the oil, right? Okay, this is a simple one. This is problem 4, right? Okay, so we know that when it floats in water, right? Let's denote this as H2O again, right? So we know that the sphere floats in water with 2/3 of the volume of the sphere submerged, right? So the buoyant force is going to be this row of water times 2/3 times our volume times G, right? And if the sphere is removed and placed in oil that has a fraction that has 3/4 the density of water, what fraction, right? So now we can say the row of oil, which is 3/4 the density of water, right? So we can just replace that times V prime times G, right? And these are going to be equivalent, right? We can cross out these G's, cross out these densities, right? And so that's just going to give us that our V prime is, times 3/4 times our V prime is going to give us 2/3 times our original volume, right? So that means V prime, the volume that's submerged, right? So that means that this is going to be 2/3 times 3/4 times our original volume, right? Oh, shoot. Times 4/3. I made this mistake too many times. And so that's going to give us 8/9, right? Which means that 8/9 of our sphere is going to be submerged when placed in oil. And that makes sense, right? We would expect, yeah, and you can even use process of elimination, right? Remember that oil has a lower density than water, right? So that means that the sphere is going to be submerged more than it is in water because the buoyant force is going to be the volume of displaced oil needs to be much higher in order to provide the same amount of buoyant force, right? And the only value that makes sense is going to be 8/9, right? This is too little, this is too little. Our sphere is not suspended in place in the middle of the oil. And that kind of makes sense, but it's just nice to whittle down on everything, right? All right, so next, a YouTube, and I forgot to write this down, but these two questions, these two are part of the same set, right? Okay, so YouTube manometer, big term, consists of a uniform diameter cylindrical tube that is bent into a U shape. Thank you, FMA, for making your vocabulary as confusing as ever. It is originally filled with water that has a density of a row of water. I'm going to actually write this with a W now because only that problem starts to get weird. So the total length of the column water is L. Ignore surface tension and viscosity. Water is displaced slightly, so one side moves up a distance x and other side lowers the distance x. So find frequency of oscillation. So there's actually two ways of doing this, right? First way is default, like actually doing this problem out, and I'm going to show you how to do that later. But second way, I'm actually going to show you right now. I'm going to take a screenshot of this, of all these answer choices, and we can go back here, right? And I'm just gonna, as web, I think this is how I do it. Right, okay, so this can actually be whittled down to a kind of process of elimination thing, right? So first of all, we need to remember that this is frequency, right? Frequency of oscillation. Our frequency has units of 1 hertz, right? So it's going to be 1 divided by our time. So let's look at these values, right? We have density is going to be mass divided by volume. So we have mass divided by length cubed, right? And we have our gravity, our gravitational acceleration. Remember that's m over meters per second squared, right? So that's going to be length divided by time squared, right? And so finally we have our length, right? And that's just going to be a length. Remember that. So I think from what I saw, I think this is just going to be going by the fact that so that works, right? 5, 5. It's a. So this is going to go by a kind of process of elimination with remember dimensional analysis. That's where this actually comes in, right? And so what we can do here is, that is not the right thing, 2015, 19. And so if we go down here, yeah, so remember that our frequency is going to be 1 over a time unit, right? So we can denote this in dimensions by saying that this is going to be equal to 1 over t, right? And so that means, first, c is wrong. This goes by, let's look at c, right? That's 2L over g, square root of that, right? And that's going to be equal to, let's just denote this into dimensions. That's going to be some constant times L divided by L divided by t squared, which is going to be the square root of t squared, which is going to be a t. So that would just be in seconds, not 1 divided, not hertz, right? So we know that c is wrong. I'm pretty sure the rest of these go by the same constant. The majority of these go by the same constant. So I'm going to keep these, actually. And so 1 over t, right? And so we know that c is wrong. Next one, we have L over t squared divided by m divided by L cubed, right? And we can already tell that this is not going to work out, right? We're going to have this mass, we're going to have this remaining, and just a lot of problems. So that means that D is wrong as well. So let me erase this, and so we can cross that out. Finally, we have mass divided. Okay, so anything with density isn't going to work because we have this extra mass, and we really can't eliminate that. So that's also wrong. So now we're limited to these, and the premise that I think they used was that frequency, since it's 1 divided by time, 1 divided by our period, that means that it's always going to have this 1 over 2 pi times this. And there's no way this is going to conjure up like 4 pi squared, right? And so that means that B is also incorrect, giving us A, right? And so that's the kind of process of elimination tactic that they use. The other approach is going to be actually using this and actually doing this mathematically, right? So remember from last time, the oscillation time, where we had this formula, right? 2 pi times the square root of x over a, where x is some kind of displacement and a is some sort of acceleration, right? That means our frequency, which is 1 divided by our period, is going to be 1 over 2 pi times the square root of a divided by x, right? We're already seeing that we're given this displacement of just x, right? So we can say that our acceleration is equal to force divided by mass. And let's find what force and mass are independently. First of all, our force is going to be our mass of this portion of water, this volume of water, height of 2x. Remember, it's moving down and up by x, right? So that means that we're going to have a total height of 2x for these combined together. So that would mean that this is going to be rho times our volume, which is going to be 2x times our cross-sectional area times g, right? Next, we know that our mass is going to be the entire mass of the U-tube or whatever, right? And just for a little bit of a reference, remember that our tube is going to look something like this, right? Where in this case we have this, and we're having some sort of displacement of x on both sides, right? So the entire mass is going to be changing, right? So that's going to give us rho times our volume, which is just the length times our area, right? That's what this is going to be based off of. And so now we know that our, let's just first move this. If I'm talking too fast, I'm sorry. I'm kind of a little bit wonky today. And so from this, we know that our acceleration is going to be equal to our force divided by our mass, which is going to be, what is this, rho times 2x ag divided by rho la, right? Cross these, and then once we plug it into our frequency, that's going to be 1 over 2 pi times our acceleration, which is 2xg divided by L divided by x, right? And we can just cancel out this, excuse me, cancel out these two x's, and so our frequency is going to be 1 over 2 pi times the square root of 2g over L, right? And if we check back on our worksheet, sorry for the delay, but we've actually solved this twice, and that's going to just give us a, which is 1 over 2 pi times the square root of 2g over L, right? Okay, next, oil with, so this is the second part of this problem, remember? So oil with a density half that of water is added to one side of the tube until the total length of oil is equal to the total length of water. Thank you for your clear wording. Determine the equilibrium height difference between the two sides, right? And so this is quite an interesting problem. So let's say that we can kind of understand what they're saying, right? So we have, this is a great illustration, by the way, if you can tell. So let's say we have some amount of water here, right? We have some amount of water here, and we have some amount of water here. And I'm going to color all this in because I'm a good boy. And this is going to have a height of L, right? So density, so oil is added to one side of the tube. Let's say oil is added into here until the total length of oil is equal to the total length of water, right? So we're just adding oil, right? We're adding some amount of oil. Oh, that's very bright, actually. I don't like that color. Is this better? Close enough. So we're adding oil into here until we have some sort of new length of oil. That's also the length of the current amount of water, right? So let's draw a new illustration of how this will look. Oh no. So now we're gonna have a very nice looking manometer with some amount of oil of length L, right? We're gonna have some amount of oil length L, and then we're gonna have some amount of water here, right? And so I'm pretty sure what it means by length L is like the total amount of water that's added. Yeah, so the total length of the column water is going to be L. So this is actually incorrect. This would be like this entire length is going to be L, right? So that means that once we add L, this part is still going to total out to be L, right? But the interesting thing is now we have some sort of mass, right? We know that this is going to be in equilibrium. So we have some amount of oil here, some amount of water here, and the mass of this amalgamate of oil and water is going to be equal to the mass of the water on the other side, right? That's what it means to be in equilibrium. So let's think about how this would work, right? So this length of oil, since it has half the density of water, it's also going to have half the mass of water, right? So let's say that we have half the mass of water, which we can denote as this, right? Plus the mass, some mass of water, plus some mass of water is going to be the total mass of all of this fluid, right? It's going to be the mass of this oil plus the mass of all this water, right? And so that means that the total mass that we have in the system is going to be equal to 3 over 2 times the mass of water, right? We know that both of these sides are going to have the same amount of mass to be in equilibrium. So we know that this side is definitely, this side of pure water is going to have half of this total amount of water, right? So that's going to be 3 over 4 times the mass of water, right? And this side is also going to have 3 over 4 mass of water, right? But we know that this this portion of oil is going to have 1 over 2 times the mass of water, right? Which means that the remaining amount is going to be 1 over 4 times the mass of water, right? So that means that we have some length of water and some length of oil, right? And we know that the length of water is going to be 1 over 4L on this side, right? And going by that logic, we know that there's going to be 3 over 4 times the length of water here on the other side, right? So that means, I'm sorry if the diagram looks a little bit messy. If you want a more in-depth explanation, I would suggest you just search it up, or just let me know in the comments, or just let me know in person. And so that means that on the left sides, we're going to have the length of oil plus 1 over 4L, which is going to be the length of this amount of water here. And on the right side, we're going to have 3 over 4 times the length of the water, right? And so to find the equilibrium difference, we just subtract these. So this is going to be 5 over 4L minus 3 over 4L, which is going to give us 1 over 2L, right? Or L over 2. And if we look back at our worksheet, that's going to give us answer choice B, which is L over 2, right? All right, next. 3 cubical blocks of the same volume are made out of wood, styrofoam, and plastic. When the plastic block is placed in water, half the volume is submerged, right? If the wooden block is placed in water with the plastic block on top, oh no, what did I done? I think nothing big, right? I can still draw. So, if the wooden block is placed in water with the plastic block on top, did I finish my original sentence? I'm going to pretend I did. The wooden block is just fully submerged. Similarly, if the styrofoam block is placed in oil with the plastic block on top, styrofoam block is just fully submerged. Density of oil is 0.7 times that of water. What's the ratio of density of wood to the density of styrofoam, right? So this is going to go by the fact that these are just fully submerged. Going by those 3 words, which means that the buoyant force, right, is going to be completely equal to the gravitational force, right? Or like the weight. So we know that the density of wood, so this is going to be kind of the specific gravity stuff. So if the density of our material divided by the density of our water is equal to 1, that means that it's just fully submerged, kind of going by that fact. If this is greater, where did my mouse go? Oh. If this is greater than 1, then it'll sink. If it's less than 1, then it'll float, right? But if it's just equal to 1, then it's just fully submerged. That's what it's talking about, right? So let's start working on this. First of all, when the plastic block is placed in water, half its volume is submerged. So that means that 1 over 2 times rho of Vg for a plastic is going to be equal to, wait, no, this is wrong. Plastic Vg is going to be equal to 1 over 2 times the density of water, Vg, right? And so the entire premise, we can eliminate these, and I won't be including these for the remainder of this problem, because it's just going to be these kind of comparisons, right? So we know that the density of our plastic is going to be 1/2 of the density of our water. And I'm just going to write that on the side as kind of the first thing that we proved, right? So let's get purple out here, right? So first point, we know that our rho of our plastic, and I'm just going to denote that as PL, is going to be 1 over 2 that of H2O, which I'm just going to do, yeah, right? All right, next. If our wooden block is placed in water with a plastic block on top, wooden block is just fully submerged. So that means that our wood, right? Wood times volume times gravity plus density of plastic times volume times gravity is going to be equal to density of water times volume times gravity, right? And I said that I wouldn't include them, but I'm including them here just for proof, right? We know that the density of our plastic is 1 over 2 times the density of our water. And I'm just going to cross out all the VGs. So that would mean that that the density of our wood plus 1 over 2 times the density of our water is going to be equal to the density of our water, right? And we can just move this to this side, which means that our density of our wood is going to be equal to 1 over 2 times the density of our water. So same thing as plastic, basically. And so I'm just going to write that equation up here again. So now we found out that our wood is going to be also 1 over 2 times the density of our water, right? Third, if the styrofoam block is placed on oil with plastic block on top, styrofoam block is just fully submerged. Density of oil is 0.7 times that of water, right? So we know that our oil is going to be 0.7 times our water, right? Which means that our plastic, which is 1 over 2 our density of water, is going to be, and we can just write that here, 1 over 2, we're going to have to do 1 over 2 times the density of water multiplied by what I believe to be 10 over 7, right? Times density of water to find the density of plastic in oil, right? So density of plastic in oil, like compared to oil, is going to be, right? So this is going to be going by this kind of thing, right? So our density of plastic is going to be 5/7 the density of oil. And so if we write, we can write that here after this, which means that our density of our plastic is going to be 5/7 that of our density of oil, right? And so that means that when we put, what did it say? When we put our styrofoam block and our plastic block together, it's fully submerged. So again, so our row of plastic plus our density of oil, not our oil, styrofoam, you gotta love writing, is going to be equal to the density of our oil, right? So we can start replacing some stuff. So density of plastic is 5/7 the density of our oil, right? And we could have actually written this a different way. We could have said plastic is going to be 1 over 2 of our density of water plus our density of styrofoam, which I'm just going to do that, is equal to 0.7 times the density of our water, right? So that means that our styrofoam is going to be 0.2 times the density of our water, right? And yeah, we can actually solve it from there. There's also a different way of doing this, which is we could say that our plastic has a density of, we could say that since it has 5/7 the density of oil, we could say something like this, right? Plus styrofoam is going to be equal to oil, and we know that styrofoam is then 2/7 the density of oil, and then we can compare that, and that just takes a bit more math and a bit more working that I'm too tired to deal with right now. So we can just go here. That means that our fifth part is that our density of styrofoam is going to be equal to 0.2, so 1 over 5 times 1 over 5 the density of our water, right? And so what do we want? The wood divided by our styrofoam, right? So the problem is asking for this ratio. And so that's just going to be 1 over 2 times the density of water divided by 1 over 5 times the density of our water. We can eliminate these. That's just 0.5 divided by 0.2. Basic math, and that's just going to be equal to 2.5, right? And so if we, for the final time, if we go back to our worksheet, that's going to give us A, which is 2.5. And that rounds off the video for this week. Sorry that this took a little bit longer than usual. This is a pre-recording, and I kind of wasn't prepared for this. But that's basically it. Thank you so much for attending, and next week, yeah, I'll see you next week.